right, chapter 14 is about probability. We're talking like basic probability, but we're not even doing probability today. We're going to talk about some definitions of some things. All right. So you know how your textbook has like an example that you the entire chapter in every chapter? It's really gotten a little intense in this chapter. Like if you can't even like read this chapter without having read the example, because if not, you have no idea what they're talking about. So in chapter 14, they're saying you're driving from home to school every day, and you feel like you always hit this red light. Isn't that annoying? That happens to you and Marianne 641 all the time, I'm sure. So you always hit this red light. So they're trying. You're like, okay, well I'm going to start tracking this because I want to know how often I hit this red light. Okay. So thinking about what's random in the situation, right? Is you're driving the random part, or is it the light turning red and green and yellow the random part? Does it depend on you driving, or does it depend on the light? The light's on a timer, right? It's just we're saying we're going from school to every day. We're always seeing this red light. The red light's on a timer, right? So that's not necessarily random, but are you leaving your house the exact same moment every day? Are you driving the exact same speed every day? Are you behind the same amount of cars on the way to school every day? All of those things aren't constant. So what's really happening is your driving is the random part. Okay? So, again, we want to figure out what's happening. So we start tracking it. We start saying every day we're going to record if the light is red or green. Okay? So, this graph is a cumulative percentage. Okay? So the first point is 100%, looking at percent green, because the first day that you recorded it, there was a green light. So the percent of the time that was green is 100%. The second day, there was a red light. So now the percentage of time that it was green is 50%. Yeah, so we're doing a cumulative percentage. So eventually you can see it starts evening out, right? So that's what's happening with probability. You know how we say there is like a 50% chance of heads and tails? Well, if you didn't know that probability, you were trying to figure that out, you would flip a coin a bunch of times. Like the first time you flipped it, you're trying to get percent heads, let's say. First time you flip it, you get a head. That's 100% of the time it's heads. But then over time, when you start keep flipping it, you realize it's getting closer and closer to 50% of the time that it's heads. All right, that's how we get those probability numbers that we know. Like when you roll a die, you get a 1 a sixth of the time. Because if you roll a die over and over and over again, you do a cumulative percentage of how many times that happens, that you get a 1, you get closer and closer to a sixth. All right, that's where those numbers come from. Okay? So, every time you go up to the light, or every time you roll the die, every time you flip the coin, that's going to be a trial, just like in chapter 11. And at the end of every trial, there's an outcome. The light was red, the light was green, the die is 1, the coin is heads. Okay? Just making sure you remember those vocabulary words. And then when you combine the outcomes, you end up getting an event. So in this case, every day you get to the light is an event. If you were doing flipping 2 coins, then we both the coins, that's an event, right? And then the sample space is just going to be all of the possible outcomes. So when you roll a die, just one die, what are all of the possible outcomes? Right, 1 through 6. Those are the possible outcomes. So we'll talk some more about that in a second. Now, if you're assuming, which we are in this chapter, that your events are independent, meaning they aren't related to one another. So every day you're driving from home to school is not influenced by the day before. It's a separate event. Does that make sense? That's what independent would mean in this case. All right? So it's completely separate from the day before. When you're rolling the die before had nothing to do with rolling the die now. All right? Independent events. But we have this thing called the law of large numbers. And it says that as the number of independent trials increases, the long-run relative frequency gets closer and closer to a single value. So that graph we saw earlier, that's just showing the law of large numbers. the long run relative frequency gets closer and closer to a single value. So remember how I said that's how you get the 50% heads, the 1/6 one on the die? That's where we get those probabilities, and that's what we call those empirical probabilities, all right? Because over time, if you kept doing the same action over and over and over again, those probabilities get closer and closer to a single value, single percentage, all right? That's what that's called, law of large numbers. That's something in the long run, so make sure you know that's in the long run. Now, there's also things that we do that are not valid ways of thinking. You know, in like a baseball game, let's say a batter comes up to bat and he strikes out. And the next time he goes up to bat, he strikes out. And he keeps striking out, and he's striking out for like 6 games in a row. People start saying things like he's due for a hit, right? Every single time he goes up to bat, is that an independent event? Yes, there's nothing to do with the last time he went to bat, right? It's a new event. So since it's independent, is that really a sound way of thinking that he's due for a hit? No, it's something that we say, but it's not something that's statistically true, okay? So people want to use, it's called the law of averages, that eventually everything will average out. But that is not a valid statistical way of thinking, all right? Every one of those events is independent. It doesn't influence the one from before. So theoretically, this guy that's going up to bat could never get a hit ever again, right? He'd strike out every time he goes up to bat. That could happen, okay? So we don't want to use the law of averages. And whenever we see a statement using the law of averages, we want to say why that would be untrue. So for example, one common proposal for beating the lottery is to know which numbers have come up lately, eliminate those from consideration, and bet on numbers that have not come up for a long time. Proponents of this method argue that in the long run, every number should be selected equally often, so those that haven't come up are due. Explain why this is faulty reasoning. Every time they draw the lottery numbers, they put them back in, right? So you could, again, theoretically, get the same exact lottery numbers the next time, right? So again, there is no such thing as it's going to come up when you have all these independent events, okay? So you would say something along the lines that the reasoning is faulty because the law of averages does not exist, okay? And the lottery numbers could be the exact same the next time, just as easily they could be completely different, all right? So keep in mind, law of averages is not a statistical way of talking about things. All right, a few examples really fast, and then I'll give you the assignment. So the first one, we're talking about sample spaces. So again, sample space is just all the possible outcomes. It's getting you to think about some things we're going to do with probability tomorrow. But so for the first one, we're just writing out the sample space. We're going to toss 2 coins and record the order of heads and tails. So what are the possible outcomes? Heads, heads, tails, tails, heads, tails, but there's one more because we're recording the order, right? So tails, then heads. So make sure you're thinking about this scenario, right? If they weren't recording the order and it didn't matter, then there's only 3 possibilities of what could happen. But since we're recording the order, then heads, tails, and tails, heads are 2 different outcomes. Does that make sense? In the second one, a family has 3 children. Record the number of boys. So what is the possible number of boys? 1, 2, 3, or 0, right? You could have all girls. Questions about B? All right, on C, flip a coin until you get a head or 3 consecutive tails, and you're going to record each flip. So you flip the coin once, and you get a head. Does that mean you have to stop? Yeah. You flip a coin until you get a head. So we stop. All right, what if the first time we get a tails and the second time we get heads? Then we stop. Or when you have tails and then heads, and then we would stop. Or we have tails, tails, and tails, and then we would stop because it says to get heads or 3 consecutive tails. So that's our sample space. Yes? The last one is roll 2 dice, record the larger number. So if you're rolling 2 dice, what's the smallest number you could get? 1, because you could roll 2 ones, and so the larger number would be a 1. You could roll 2 and get a 1 and a 2, so 2 would be larger, right? And the rest of these, in all the scenarios, you could get 3, 4, 5, or 6, right? You're just rolling the 2 and recording which one's bigger. So to understand sample space, because that'll help you tomorrow. All right, 2 little questions here. And number 3, a casino claims that its roulette wheel is truly random. What should that claim mean? What does truly random mean? Right. Every section on the wheel, because the roulette is wheel, has an equally likely chance of being selected, even if it's landed on sounds weird, each spin. So again, theoretically you could get 00 10 times in a row. Equally likely chance each time if it's truly random. Alright, last question. Comment on the following quotation. What I think is our best determination is it will be a colder than normal winter. She's a climatologist. I want to point that out, climatologist. I'm basing that on a couple of things. First, in looking at the past few winters, there has been a lack of really cold weather. Even though we are not supposed to use the law of averages, we are due. So, what should we say about this? I don't know. She just said that. Plus, she's a climatologist. That's the first thing she looked at to decide if we're going to have a cold winter or not. It's her degree. That's like her career. I'm just saying. Wouldn't you be able to look at something else first, like other patterns? I don't know. Not. Looks like we're due. So that's what I'm going to say in the Associated Press. Yes. Yes. 1992. All right. Do these make sense? Yes? This is your assignment then. 2, 4, and 6.